Your understanding of grounding grids is generally correct. The purpose of a grounding grid is to provide a low-impedance path to ground for fault currents and lightning surges. A grounding grid that meets the National Electrical Code, or NEC, requirement of 25 ohms or less is typically sufficient for most systems, regardless of size. Adding more power should not affect the impedance of an existing grounding grid unless it significantly increases the ground current, which is unlikely. Bonding is the process of connecting metal surfaces together to create a continuous electrical path. Improper bonding can lead to potential differences between grounds, as you have observed. Upgrading a system may require adding additional bonding jumpers to ensure proper connectivity between all electrical components, but this alone should not affect the adequacy of the grounding grid. There may be other potential issues contributing to the grounding problems you are experiencing. Firstly, degradation of bonding connections. Over time, bonding connections can loosen or corrode, increasing impedance. Secondly, incomplete or improper bonding. Not all metal surfaces may be properly bonded, creating isolated areas with potential differences. Thirdly, design deficiencies. The original grounding and bonding system may not have been designed for the current load or system size. Fourthly, local soil conditions. Soil conditions can affect the effectiveness of the grounding grid. I can provide some recommendations. Inspect all bonding connections and ensure they are tight and secure. Verify that all metal surfaces, including equipment frames, conduit, and cable trays, are properly bonded. Contact a qualified electrical engineer to evaluate the grounding and bonding system and determine if any design modifications are needed. Consider lower ground resistance values, for example, 5 ohms or less, for improved power quality and safety. To elaborate on the function of a grounding grid, consider its primary roles. It's there to provide a low impedance path for fault currents, allowing protective devices like circuit breakers to quickly trip and clear faults. It also provides a path for lightning surges, diverting them safely to the earth and preventing damage to equipment. A grounding grid that meets the NEC requirement of 25 ohms or less is generally adequate, and the value is a maximum, and lower values are always better. The NEC stipulates minimum requirements, and often exceeding those requirements provides a safer and more reliable system. Now, let's consider why adding more power shouldn't, in theory, affect the grid's impedance. The impedance of the grounding grid is primarily determined by its physical characteristics such as the size and spacing of the conductors, the depth of burial, and the soil resistivity. Unless you are dramatically altering the ground current levels, the grounding grid's fundamental impedance should remain relatively stable. When we talk about bonding, we're talking about creating a continuous, low impedance path for current to flow between all metal parts of the electrical system. This includes equipment enclosures, conduit, cable trays, and even structural steel in some cases. Proper bonding is crucial to ensure that if a fault occurs, the fault current can flow back to the source quickly and safely, again trapping the overcurrent protection. Improper bonding can lead to a scenario where different metal parts are at different electrical potentials. This is precisely what you are observing with the 40 volts to 50 volts potential difference between grounds. That voltage difference can be dangerous and can also cause equipment malfunction. Upgrading the system by adding more bonding jumpers is a good practice, but it's important to ensure that these jumpers are properly sized and installed. They must be large enough to carry the potential fault current, and they must be securely connected to clean, corrosion-free surfaces. The size of bonding jumpers is determined by NEC Table 250.102. Now, let's explore some of the possible causes for the grounding problems you're experiencing. Degradation of bonding connections is a common issue. Over time, connections can corrode, loosen due to vibration, or simply become compromised due to environmental factors. This increases the impedance of the connection, hindering the flow of fault current. It's important to periodically inspect and test these connections to ensure they are in good condition. Incomplete or improper bonding is another frequent culprit. It's possible that some metal surfaces were simply overlooked during the initial installation, or that the bonding was done incorrectly. For example, A bonding jumper might be connected to a painted surface, which is an insulator and prevents proper electrical contact. All bonding connections should be made to clean, bare metal. Design deficiencies can also be a contributing factor. It's possible that the original grounding and bonding system was not adequately designed for the current load or the physical layout of the facility. For example, the grounding conductor may be undersized, or the bonding jumpers may be too long, which increases impedance. Finally, local soil conditions can play a role. Soil resistivity varies depending on the type of soil, its moisture content, and its temperature. High soil resistivity increases the impedance of the grounding grid, making it less effective. If you suspect that soil conditions are a problem, you can consider using ground-enhancing materials to improve the conductivity of the soil. Let's delve deeper into the recommendations for troubleshooting your grounding problems. A thorough inspection of all bonding connections is paramount. Look for signs of corrosion, looseness, or damage. Use a torque wrench to ensure that all connections are tightened to the manufacturer's specifications. If you find any questionable connections, clean them thoroughly and retighten them. When verifying that all metal surfaces are properly bonded, pay close attention to equipment frames, conduit runs, and cable trays. Ensure that there are bonding jumpers connecting these items to the grounding system. Also, check that the bonding jumpers are properly sized according to NEC Table 250.102. If you are unsure about the adequacy of the grounding and bonding system, it's always a good idea to consult with a qualified electrical engineer. An engineer can perform a thorough evaluation of the system, including impedance testing, and can recommend any necessary modifications. Furthermore, while the NEC requires a maximum ground resistance of 25 ohms, striving for a lower value can significantly improve power quality and safety. A lower ground resistance provides a more effective path for fault currents and lightning surges, reducing the risk of equipment damage and electrical shock. Aiming for a ground resistance of 5 ohms or less is generally considered a best practice. There are several ways to achieve a lower ground resistance. You can install additional ground rods, expand the size of the grounding grid, or you use ground-enhancing materials. Ground-enhancing materials are typically composed of minerals that improve soil conductivity, thereby reducing ground resistance. In addition to the physical inspection of bonding connections, it's also beneficial to perform electrical testing to verify the integrity of the grounding system. Ground impedance testing can be used to measure the impedance of the grounding grid. This test involves injecting a current into the grounding system and measuring the resulting voltage drop. The impedance is then calculated using Ohm's law. Low impedance is desirable, indicating a good grounding path. Continuity testing can be used to verify the continuity of bonding connections. This test involves passing a current through the bonding connection and measuring the resistance. Low resistance indicates a good connection. High resistance indicates a problem that needs to be addressed. Furthermore, understanding the difference between grounding and bonding is essential for troubleshooting grounding problems. Grounding refers to connecting the electrical system to the earth, providing a reference point for voltage and a path for fault currents. Bonding refers to connecting metal parts of the electrical system together, creating a continuous electrical path. While both grounding and bonding are important, they serve different purposes. Grounding provides a path for fault currents to return to the source, while bonding ensures that all metal parts are at the same potential, reducing the risk of electrical shock. To further explain the importance of low impedance grounding, consider the effects of high impedance. High impedance in the grounding system can impede the flow of fault current, causing overcurrent protection devices to operate slowly or fail to operate at all. This can lead to prolonged fault conditions, which can damage equipment, create fire hazards, and increase the risk of electrical shock. Conversely, low impedance in the grounding system allows fault currents to flow quickly and easily, causing overcurrent protection devices to operate promptly and clear the fault. This minimizes the risk of equipment damage, fire hazards, and electrical shock. When evaluating the adequacy of a grounding system, it's important to consider the specific requirements of the equipment being served. Some equipment, such as sensitive electronic devices, may require a lower ground resistance than what is mandated by the NEC. In these cases, it may be necessary to install a dedicated grounding system for the sensitive equipment. Also, it's crucial to maintain accurate records of all grounding and bonding system modifications. This includes documenting the location of ground rods, the size and type of grounding conductors, and the date of installation. These records can be invaluable when troubleshooting grounding problems in the future. To reiterate, a well-designed and properly maintained grounding and bonding system is essential for electrical safety and equipment reliability. It provides a path for fault currents, protects against electrical shock, and minimizes the risk of equipment damage. If you are experiencing grounding problems, it's important to take them seriously and address them promptly. Start by inspecting the bonding connections, verifying that all metal surfaces are properly bonded, and consulting with a qualified electrical engineer if necessary. By following these steps, you can ensure that your grounding system is providing the level of protection that you need. Remember, the NEC establishes minimum requirements for grounding and bonding. Exceeding these requirements and striving for a lower ground resistance is always a good practice. A lower ground resistance provides a more effective path for fault currents and lightning surges, reducing the risk of equipment damage and electrical shock. The condition of the soil surrounding the grounding electrodes can significantly impact the overall effectiveness of the grounding system. Soil resistivity, which measures how well the soil conducts electricity, varies depending on factors like moisture content, temperature, and chemical composition. Dry, sandy soil typically has higher resistivity, while moist, clay-rich soil has lower resistivity. High soil resistivity increases the impedance of the grounding system, making it less effective at dissipating fault currents and lightning surges. In areas with high soil resistivity, it may be necessary to take additional measures to improve the grounding system's performance. This can include installing additional ground rods, using ground-enhancing materials, or chemically treating the soil. Ground-enhancing materials are designed to improve the conductivity of the soil surrounding the grounding electrodes. These materials typically consist of minerals and chemicals that attract and retain moisture, which helps to reduce soil resistivity. Chemical treatment of the soil involves adding chemicals to the soil to improve its conductivity. However, this method should be used with caution, as some chemicals can be harmful to the environment. Furthermore, the proximity of other underground utilities can also affect the performance of the grounding system. Underground pipelines, cables, and other metallic structures can interfere with the flow of fault currents, increasing the impedance of the grounding system. It's important to be aware of the location of these utilities when designing and installing a grounding system. The depth at which grounding electrodes are buried also affects their performance. Ground rods should be buried deep enough to reach moist soil, which provides better conductivity. The NEC specifies minimum burial depths for grounding electrodes. In addition to ground rods, other types of grounding electrodes can be used, such as ground plates and ground rings. Ground plates are flat metal plates that are buried horizontally in the ground. Ground rings are circular conductors that are buried around the perimeter of a building or structure. The choice of grounding electrode depends on the specific site conditions and the requirements of the electrical system. Also, surge protection devices, or SPDs, can be used to protect equipment from voltage surges caused by lightning or other electrical disturbances. SPD are installed in parallel with the equipment they are protecting and divert surge currents to ground. A properly designed and installed grounding system is essential for the effective operation of SPD. It is recommended to conduct regular inspections and maintenance of the grounding system to ensure its continued effectiveness. This includes visually inspecting grounding electrodes, conductors, and connections for signs of corrosion or damage. It also includes testing the ground resistance to ensure that it is within acceptable limits. The frequency of inspections and maintenance depends on the environmental conditions and the criticality of the electrical system. In harsh environments, such as coastal areas or industrial facilities, more frequent inspections may be necessary. In addition to visual inspections and ground resistance testing, other types of testing can be performed to evaluate the performance of the grounding system. These tests include impedance testing, continuity testing, and step potential testing. Impedance testing measures the impedance of the grounding system, which is an indication of its ability to dissipate fault currents. Continuity testing verifies the continuity of grounding conductors and connections. Step potential testing measures the voltage gradient in the soil around grounding electrodes. This test is used to identify potential shock hazards. The results of these tests can be used to identify areas where the grounding system needs to be improved. Finally, the design and installation of a grounding system should be performed by qualified personnel who are knowledgeable about the NEC and other applicable standards. Improperly designed or installed grounding systems can be ineffective and even dangerous. It is also important to document all aspects of the grounding system, including the location of grounding electrodes, the size and type of grounding conductors, and the results of any testing that is performed. This documentation can be valuable for future maintenance and troubleshooting.